In the cold, seemingly empty expanse of space, there lies a planet that, at first glance, appears to be little more than a forgotten rock. Yet, this planet, Mercury, holds a profound mystery that has confounded scientists for decades. It is the smallest planet in our solar system, barely larger than our moon. A world constantly battered by the sun's intense heat and radiation. Its surface, pocked and scarred, bears the marks of billions of years of cosmic history. And yet, within this desolate world exists an enigma that challenges everything we know about planetary science: a magnetic field. A weak one, certainly, but one that is undeniably present, and one that holds the key to understanding the planet's deep history. Mercury sits in the most extreme environment in the solar system. Its day and night temperatures swing wildly, from scorching highs of over 800 degrees Fahrenheit to freezing lows of nearly minus 330 degrees Fahrenheit. A planet exposed to unrelenting solar radiation. And yet, despite these inhospitable conditions, it harbors an astonishing feature: a magnetic field. A planet so small, so close to the Sun, and with a rotation so slow, it seems improbable that Mercury could possess anything resembling a magnetic shield. And yet, it does. One that has both mystified and intrigued scientists since its discovery. What causes this magnetic field? And more importantly, what does it tell us about Mercury's past, its core, and its future? Magnetic fields are one of the most fundamental phenomena in the universe. They govern everything from the orbits of particles in space to the behavior of entire solar systems. Planets with magnetic fields experience a form of protection, an invisible shield that redirects the harmful particles of the solar wind and keeps their atmosphere intact. This field is generated by a process called the dynamo effect, where a planet's molten core generates electrical currents, which in turn create magnetic fields. Earth, with its large, fully liquid iron core, is a prime example, producing a strong and protective magnetic field that shields us from the harmful effects of the sun. But Mercury? Mercury's field is weak, much weaker than Earth's, but its presence still reveals something extraordinary. The question is, how does a planet so small, with a core vastly different from Earth's, manage to create a magnetic field at all? In 2011, NASA's Messenger spacecraft arrived at Mercury, tasked with solving one of the most perplexing mysteries of the solar system. Over 4 years, the spacecraft mapped the planet's surface, studied its composition, and measured its magnetic field in unprecedented detail. The findings were unexpected. Mercury's magnetic field, though weak, was not random or insignificant. It was structured and organized, creating a distinct magnetic environment that interacted with the solar wind. But even more intriguing, Mercury's field was not only present, it was active, fluctuating, and responding to changes in the solar wind, suggesting an ongoing dynamo process deep within the planet. Yet the puzzle remained. How does this weak field persist when Mercury's core is so much smaller than Earth's? The answer lies deep within the planet's core. Mercury, like Earth, has an iron-rich core, but it's much smaller. And unlike Earth, whose core is fully liquid and convective, Mercury's core is only partially molten. Much of it is solid. It's this smaller, partially solidified core that is responsible for Mercury's weak magnetic field. As the planet cooled over billions of years, its core began to solidify, limiting the convection currents that drive the dynamo effect. The outer layer of the core, though still partially liquid, simply doesn't have the same energy as Earth's core, and the dynamo is far weaker. But even this subdued dynamo is enough to generate a magnetic field. albeit a faint one. Mercury's dynamo is a shadow of what it might have been. In Earth, the dynamo is driven by the motion of liquid metal in the outer core, creating powerful electric currents that generate the planet's strong magnetic field. On Mercury, however, the outer core is only partially liquid, and the planet's smaller size means it has less material to drive the dynamo. This limits the strength of the magnetic field. But despite these limitations, there is still enough motion within the molten part of the core to generate a weak, yet persistent, magnetic field. Despite its faintness, Mercury's magnetic field has a profound impact on its environment. The solar wind, a constant stream of charged particles from the sun, bombards the planets with immense force. On Earth, our magnetic field deflects the solar wind, protecting our atmosphere and shielding us from harmful radiation. On Mercury, however, the magnetic field is much weaker. It doesn't offer the same level of protection as Earth's, but it still plays a crucial role. The solar wind interacts with the planet's magnetic field, creating a dynamic interaction that pushes charged particles into the planet's exosphere. This interaction has had a profound effect on Mercury's thin, wispy atmosphere, preventing it from growing thick or dense over time. This interaction between Mercury's magnetic field and the solar wind may explain why the planet has such a thin atmosphere. The solar wind, over billions of years, has slowly stripped away Mercury's atmosphere, leaving behind a tenuous exosphere. A thin layer of atoms and molecules that are constantly being replenished by solar wind collisions and outgassing from the planet's surface. But the magnetic field still provides some protection, diverting the solar wind and preventing a complete atmospheric loss. However, this delicate balance is slowly deteriorating as Mercury's magnetic field weakens with time. Could Mercury's magnetic field have been stronger in the distant past? Scientists believe that when Mercury was younger, its core may have been more active, more molten, and more capable of generating a stronger magnetic field. In those early days, the dynamo may have been more vigorous, providing more robust protection against the solar wind and allowing Mercury to retain a thicker atmosphere. But as Mercury's core cooled over billions of years, the dynamo slowed down and the magnetic field weakened. This is a pattern that we see in many small planets, and it's likely that Mercury is no exception. Mercury's magnetic field may be a relic of the past, an echo of a time when the planet was more dynamic and full of internal heat. As the core cooled, the dynamo effect slowed, and the magnetic field weakened. But even as the field fades, it continues to tell the story of the planet's deep history. In a sense, Mercury's magnetic field is like a planetary fossil, a surviving trace of the planet's geological and thermal evolution. As Mercury's magnetic field continues to weaken, we may be witnessing the slow death of a planet's protective shield, a process that could take billions of years to complete. Mercury's magnetic field is a faint but enduring mystery, a legacy of the planet's turbulent past. Despite its weakness, it is a testament to the extraordinary processes that occur deep within planets and the forces that shape them over time. It is a reminder that even the smallest, most distant worlds can hold profound secrets, secrets that can reveal not only the history of a planet, but the future of planets like it scattered throughout the cosmos. Mercury's magnetic field is more than just a scientific curiosity. It is a key that unlocks the secrets of planetary evolution, how planets form, evolve, and die. It challenges our assumptions about what makes a planet habitable, what defines its character, and what forces continue to shape its fate. As we continue to explore the mysteries of Mercury, we are reminded that the universe is full of surprises, and that even in the most unlikely places, on the smallest and most distant planets, there are still mysteries to uncover, waiting to reveal themselves to those willing to look.